I'll do a quick version of overview of Geisha. Chris showed you a lot about how to do it in WMS and a lot about WMS, uh, the features that are there for it. So I'll walk through a little bit more about Geisha and what it is, so that you sort of have a bit more background. So Geisha stands for Gridded Surface Subsurface Hydrologic Analysis. So it's a complete watershed simulation and management model. We can do a lot with it. We can do, water runoff. We can do sediment transport. We can do water quality. We're a physics-based model, meaning we're trying to solve, at the grid cell level or the, stream nodal segment level, what are the physical equations to move water or sediment or, water quality constituents from one cell or one segment to the next, right? So Gesha, as you saw with Chris's walkthrough, it's built on a grid, and this grid is sort of the foundational spatial dimensions for what happens inside Geisha. So, as you saw, you can pick that size. Chris picked a 90 meter. Sometimes 90 meters is the right size, sometimes 5 meters, sometimes 250 meter or something like that, right? It really depends on the size of the domain and what processes you're looking at resolving. But this computational grid size is the heart of Geisha and the heart of where we solve the mass, energy, and momentum conservation equations. And all of the point processes, for example, evapotranspiration, happen sort of over a grid cell. There we go. So why do we care about this? Why does this make a difference? Well, this lets us get at spatial variability. So we can be very spatially explicit about where things are in the watershed, and that can make a difference. So, rather than lumped style models where you just sort of everything sort of gets mushed together, the where can actually be quite important, and we can represent that with a gridded model like Geisha. And also, because we're solving physics-based processes, we have physically based parameters. So we can parameterize things much more simply and easily um, than other, types of models where you're sort of, engineer guessing what's the right parameter and then sort of calibrating on the backside. So I'll breeze through these kind of quickly. So as I mentioned, we can be very spatially explicit about different features. This really depends on your grid size, but if it's important, you can resolve it and we can get down to the process level. Go through these. As I mentioned, surface water hydrology, we can do surface water groundwater interaction, surface water quality, TMDL, sediment transport, contaminant fate transport. So we can do a lot of, we can ask a lot of questions and use Geisha to help us get at the answers. This is my sort of one slide overview of what Geisha can do, the different levels of processes that you can turn on, right? They're not all turned on by default. The only one that's turned on by default is overland flow. Everything else you're going to add as you go through the process of building the model. So why use Geisha? We can do flood modeling. We can look at water balance. We can look at ecological flows, and really looking at sort of getting at the processes. If you say you're adding tile drains or removing tile drains from a watershed, right? You're sort of fundamentally changing the processes that are at work in the model, in the area, right? So you need a physically based model to actually look at that and not just sort of, you know, figure out, what's your transformation differences, right? So you can, because we're process driven, you can change processes and see those impacts. As well as the location, right? Because we're spatially explicit, you can look at, for the same change in your watershed, look at where it happens and start to go, okay, what's the difference there? Walk through some of these. So here's an example. This is a watershed outside Chicago, looking at creating wetlands, doing various scenarios for watershed management throughout the regions. The bunch of farmers got together, wanted to set up a big giant wetland and work with the county and the USAs to sort of make this happen. So this was, they want to turn their fields that have a bunch of tile drains in them to a wetland, right? That obviously doesn't have tile drains in it because that wouldn't help wetland. So one of the first things I did was sort of set up a little quick example model of, for a given size wetland, everything else about the wetland is the same. If you just move it around the watershed, what difference does it make, right? If it's on the streams or right off the stream, sort of more up in the watershed, in the middle, down below, like just the where, right? The only thing difference is the where. So you can see the different scenarios I modeled here, right? And this is the impact of the where, right, on the flow, right? So we have quite dramatic changes, from 80 to 125 CMS on a flood that comes out through here, just based on where you put the wetland, right? And so that's really the power of a model like GSSHA, where we can get into the spatial locations, we can look at process changes and understand how those impact our watershed. So let me stop there.